started. A couple announcements before we start. We will have a quiz on Monday. So that's going to be just covering Chapter 2 material and Chapter 3. Today we will not quite finish Chapter 3. We'll get very, very close. So everything in Chapter 3 up to what we cover today will be on that quiz. So make sure that you've studied and you're prepared for that. We do have an exam coming up. Our first exam will cover chapters 1 through 4, and that is going to be starting a week from today. So that's going to be Friday through Monday. And so there is a sample exam to give you an idea of the format, the length of the exam, the types of questions that you'll see. And so I encourage you to take a look at that. And start working the chapter 1 through 3 problems on that, and then we'll learn chapter 4 next week, and you can continue. So today we're going to discuss how the intermolecular or non-covalent forces that we talked about on Wednesday impact the properties, the physical properties of molecules. And the two physical properties we're going to spend most of our time talking about are boiling point and solubility. Okay, so and then we have a table here that summarizes what we talked about on Wednesday. It does have ion-ion forces in here, which we didn't talk about, but you would have learned about those in general chemistry, and obviously those are very strong attractive forces. So you should understand the hierarchy of these forces, and then you should remember that even though hydrogen bonds are the strongest of our non-covalent forces, that they are significantly weaker than covalent bonds, about 20 times weaker than a typical covalent bond. Okay? All right, so how do intermolecular forces affect boiling points? Who would like to raise their hand and summarize how intermolecular forces affect boiling points? Okay, Claire?
The stronger the intermolecular force, the higher the boiling point is going to be because the more energy it takes to break those bonds.
Okay, so molecules are held together by intermolecular forces. In the liquid phase, molecules are closer together than in the gas phase. So if we're going to convert a molecule from the liquid phase to the gas phase, we're going to need to add enough energy to break up those intermolecular forces. Very good. So the stronger the intermolecular forces are, then the higher the boiling point should be. It would require more energy to break those up. So let's practice this. We have an iClicker question. Let's get out our iClickers. Go ahead and talk to your neighbors and decide which of the following molecules, based on this discussion we've just had, which of the following molecules would have the highest boiling point? All right, we give you a few more seconds maybe to come up with your final answers. Are there any more answers coming out? No. Going once, going twice. All right, I guess that's all the answers we have. So, which one has the highest boiling point? D. Why does D have the highest boiling point? Who would like to explain that to the class? Yes, please. Okay, so two molecules of D. D is an alcohol, and two molecules of an alcohol can hydrogen bond to each other, giving it stronger intermolecular forces than any of the other molecules. Okay. What about A? Could two molecules of A hydrogen bond to each other? No, why not? There's no hydrogen attached to the oxygen. Exactly, very good. Remember, we have to have a hydrogen attached to an oxygen or a nitrogen in order for a molecule to hydrogen bond to another molecule of itself. Now, when we talk about solubility in a moment, you'll recognize that molecule A could indeed hydrogen bond to water molecules, which would give it some water solubility, but it could not hydrogen bond to another molecule of itself, meaning that it only has dipole-dipole forces when you're talking about boiling points. Okay? So it's important to distinguish between molecules that can hydrogen bond to another molecule of themselves, those will have high boiling points, versus molecules that cannot do this but are able to hydrogen bond to water molecules. They'll have lower boiling points, but they will be water soluble. Okay? Question? You would look for heteroatoms. The presence of heteroatoms causes there to be polar bonds. Okay? So which of these molecules is not polar? C, right? There's no heteroatoms. All the rest of them are polar because you have oxygens or chlorine in one case. Those heteroatoms give you polar bonds, which make the molecules polar. Okay? All right, so let's look at some boiling point trends. When we have compounds with similar functional groups, these two molecules I've drawn here on the board both have ketones. Which has a higher boiling point, the one on the left or the one on the right? Maybe we should have made this the iClicker question. Yes? One on the right. Okay, so you're saying because it has a smaller surface area. Okay. So you're saying that the dipole maybe of this one is diluted because that's a reasonable thought. It's actually not the case, but it's not a bad answer. So don't feel bad about the answer. Yes. Okay. Right. So your dipole-dipole attractions will actually be pretty similar, even though they are different. This one has more longer alkyl chain. There's not going to be a very measurable difference in the dipole-dipole forces in these two molecules. So what you would do is you would turn to the surface area, and you would see that the one with the larger surface area has the higher boiling point. Okay, so that's one rule when you're looking at compounds that have similar functional groups. Larger surface area will give a higher boiling point. In this case, it actually doubles. So the compound on the right is called acetone, a very commonly used organic compound. Boiling point of 56. The one on the left would be called 3-propanone, boiling point of 102. That difference is attributed to the stronger van der Waals forces caused by the higher surface area. Okay? Let's look at the example right below. We have iodomethane, that's CH3I, and we're comparing that to fluoromethane, CH3F. Which one has the higher boiling point? Yes. Okay, why? Okay. Yeah, so you said Fluorine is more electronegative than iodine, so you're going to have a more polar bond. That's true. However, iodine has a higher boiling point. So that's the opposite of what you would expect based on the reasoning of the polarity of the bonds. And the difference is huge. Right? This is a gas all the way down to a very, very low temperature. Okay? So there's a different property other than the electronegativity and the polarity of those bonds that's important. What is it? Too many answers at once. We'll have to have someone raise their hand, but I appreciate your enthusiasm. Who would like to raise? Yes, please. It is the size. And which property did we talk about on Wednesday that's directly related to the size of atoms? Okay, it's polarizability. So the more polarizable, so this happens if we're comparing two compounds and the atoms that are different are in the same column. The more polarizable one is going to have the higher boiling point, okay? So what happens is as you bring two of these iodomethane molecules close together, the fact that the electron clouds of the iodine are further away from the nucleus makes them more polarizable, makes those electron clouds adjust more strongly to that approaching molecule in order to maximize the attractive forces. So you actually get stronger attraction due to the temporary dipole caused, or the induced dipole caused by that polarizability than you do from the permanent dipole, okay? And there's no way you could have predicted that ahead of time. Chemists had to measure these boiling points. We've measured them. We know that they're true. We can read our thermometers. And so we know that iodomethane has a much higher boiling point than fluoromethane does. And so that fact tells us that it has to be the polarizability that matters more in determining the boiling points than the polarity of the bond. Okay? Any questions about that? So two important trends. If it's the same functional group, larger surface area will give you a higher boiling point. If you're comparing atoms from the same column, then the one that is more polarizable will end up, the one that contains the more polarizable atom will have the higher boiling point. Question?
Is that always going to be whichever atom is bigger?
Yes, because polarizability is directly correlated to size. All right. Other questions? So we'll spend a little bit of time talking about melting point, not a whole lot, but melting point trends are going to follow boiling point trends because when you transition from the solid phase to the liquid phase, you are spreading the molecules out, and so you're going to have to break up the intermolecular non-covalent forces in order to do that. So you're going to have very similar trends, except for when we have symmetry. And symmetry only applies to melting points, not to boiling points. We'll talk about that in a little bit. Make sure you only apply this concept when we're talking about boiling points. Okay? So here's an example. Two alkanes or hydrocarbons. Which of these two compounds would you expect to have a higher boiling point? One on the left or the one on the right? Why would you say the right? Okay, I said symmetry only applies to melting point, and we're talking about boiling point right now. So it's going to be the left molecule. Why? Has a larger surface area, exactly. So the boiling point, this compound is called 2-methylbutane. Its boiling point is 27.7 Celsius, okay? And then this one, this is called 2,2-dimethylpropane. These are names we're going to learn next week when we get into chapter 4. Its boiling point is 9.5 Celsius. So this is a gas at room temperature. This one you have to heat up just a little bit above room temperature to get it to boil, okay? So this is what we would expect. based on the differences in surface area. However, as you noted, the compound on the right is more symmetrical than the compound on the left. And that symmetry gives this compound, the 2,2-dimethylpropane, a higher melting point. So the relationship between melting points switches. Negative 16 is our melting point here, right? So we do have to cool it down below the temperature of ice in order to get it to freeze. It's actually minus 17, but very, very close. This one, you'd have to cool down to a lower temperature than I've ever measured in order to get it to freeze, okay? So very, very big difference here. Why do you think symmetry gives this compound a higher melting point than this one? Yes, please. Okay, so you're going to have a very rigid structure. Usually solids are in crystals. And in a crystal, you're going to have your atoms packed very tightly. And a symmetrical molecule is going to be able to pack more tightly than an unsymmetrical molecule. Okay, so because of that very tight packing in a solid, then you can get more molecules of 2,2-dimethylpropane closer together, and in the end have stronger van der Waals forces holding them together than you can with 2-dimethylbutane. Because of the asymmetry here, you can't pack them as tightly. You're going to have more open space in the packing, and therefore you have less van der Waals forces in the solid phase here than you do here. In the liquid phase, the molecules aren't close enough together for that symmetry to matter, and it's only the surface area that matters. And again, we're not making this up. We can measure these values. We know the trends, and so we develop these theories to explain the trends, but we know these trends, so it is real. Questions? I will caution you, do not overuse the symmetry principle. It only applies to melting points. For some reason, when students learn it, they want to apply it everywhere. But it only applies to melting points, not to boiling points. Okay? All right, so let's talk about solubility, our other main physical property that is impacted by the types of intermolecular attractive forces that we can have between molecules. Okay? First, we need to define solubility in order to talk about it. And I'm pretty sure you've discussed it, learned it in general chemistry. The definition we're going to use in organic chemistry for solubility is the extent to which a compound, this is the abbreviation I like to use for compound, otherwise known as a solute, dissolves in a liquid. And that liquid is known as a solvent. The extent to which this happens is defined as solubility. Okay? So, what is the general chemistry rule that hopefully we've all learned in regards to solubility? Like dissolves like, exactly. Okay? So we've all learned this. Like dissolves like. What does that mean? Who can raise their hand and tell us what it means? Yes, please, Claire. Okay, so it's based on polarity, and that's also related to the non-covalent forces, right? Non-polar molecules would have van der Waals forces. So in order to really understand how it applies, we need to look at this diagram. There's a really nice figure in your book that shows what happens when an ion dissolves in water. So if you have an ion, usually you have this crystalline lattice, where you've got cations surrounded by anions and vice versa. And you've got these strong attractive forces, these ion-ion interactions, holding those crystals together. If you dissolve salt in water, what happens is you have so many water molecules present that several water molecules can surround an individual cation or anion, and they can be attracted to that ion via a new type of intermolecular force, one we haven't talked about yet, called an ion-dipole interaction. Okay? So an ion-dipole interaction is just an attractive force between an ion, could be either a cation or an anion, and a polar molecule. Okay? So these are very strong interactions. Individually, we would say they're stronger than an individual ion-dipole interaction. But because you can surround an ion with so many water molecules, the sum total of these ion-dipole interactions is going to be greater than the ion-ion interactions felt by an individual ion in one of these crystals. Okay? So for something to dissolve, it has to have stronger intermolecular forces with the solvent molecules than it does with itself. Okay? So the sum total of all these ion-dipole interactions has to overcome the magnitude of the ion-ion interactions for an individual ion in order for it to dissolve. Okay? Because it's not going to happen unless it's energetically favorable. Okay? So that's the basis of the like dissolves like rule. You have to be able to have intermolecular forces between solute and solvent in order for the solute to dissolve. Okay? If we have a nonpolar solute, it will not dissolve in water because you're not going to be able to have van der Waals forces between a nonpolar solute and water. You're not going to be able to have hydrogen bonds between nonpolar solute and water. So you drop something nonpolar in water, it doesn't mix. Oil and water don't mix. That's another thing that we learn in general chemistry or in the kitchen. All right. So questions about like dissolves like or the dissolving process. This is a great picture. It shows it really, really well and drives home the point, number one, that we have to be able to have attractive forces between solute and solvent. Number two, those attractive forces have to be greater than what the solute and the solvent have on their own. Okay? So we know that water will dissolve salts because it can have these ion-dipole interactions. Organic compounds, of course, have to dissolve in organic solvents, which could be polar or nonpolar. So here we have hexane. Hexane is a very common nonpolar solvent that will dissolve nonpolar organic compounds pretty well because of the van der Waals forces. If we have polar organic compounds, we want dipole-dipole interactions or hydrogen bonds. This is called dichloromethane. That's a good polar solvent. This one is called diethyl ether. It kind of looks like a bat when you draw it on the board, but it's actually a molecule. It's an ether with an oxygen and these two carbon chains coming off. This is known as ethyl acetate, commonly used in fingernail polish remover. It dissolves fingernail polish. It dissolves many other organic compounds as well. Okay, so these molecules we would refer to as being weakly polar, meaning they are not as polar as water, but they are polar enough to dissolve most polar organic compounds. Okay, so let's test out the like dissolves like rule. Okay, we have a crayon here, two little pieces of a crayon. What are crayons made out of? Wax. Is wax polar or nonpolar? Nonpolar. So would you expect a crayon to dissolve in water? No. We have water here. I'm dropping a crayon in. We'll swirl it around. We don't expect anything to happen. Okay. Here I have an Erlenmeyer flask with some hexane in it. Hexane right there, nonpolar. Will our crayon dissolve in hexane? It should. It might not happen instantly because our wax molecules are compressed pretty tightly together in this crayon, but we'll go ahead and drop our crayon in, our hexane. We'll swirl it around, and we'll actually set it down and then come back to it in a few minutes and see if it did indeed dissolve. Okay? All right, I should have put my safety glasses on when I was doing that. Please forgive me. Unfortunately, I'm captured on film doing something unsafe. I apologize for that. I did bring them, though. I intended to put them on. I'll put them on for the next demo. All right. So organic compounds will dissolve in organic solvents. Not totally, right? Non-polar solutes will have trouble dissolving in polar solvents and vice versa. But what about organic compounds dissolving in water? Is it possible to dissolve organic compounds in water? If they're polar, yes. What kind of intermolecular forces do we have between water molecules? Hydrogen bonds. So we would need organic compounds that can form hydrogen bonds in order for them to dissolve in water. Okay? And indeed, we do have organic compounds that can form hydrogen bonds. So there's a guideline. The guideline is at least one hydrogen bonding functional group. FG is an abbreviation I like to use for functional group. At least one hydrogen bonding functional group for every 5 carbon atoms will render a molecule soluble in water. Okay? Now, this is a guideline. It's not a hard and fast rule because solubility is not an either-or property. It's a sliding scale. Some things will be more soluble than others. Okay? So there's not a dividing line where you can say on this side of the line everything's soluble, on this side everything's insoluble. Okay? But it is useful. It's a useful guideline here. So if we have, what kind of functional groups would we have in molecules that could hydrogen bond to water? Okay, so we could have an OH. What 2 types of atoms would we have to have? Or one of these 2 types? Based on our definition of hydrogen bonding that we learned on Wednesday? Oxygen or nitrogen, exactly. So we need to look for an oxygen atom or a nitrogen atom in order to have functional groups capable of hydrogen bonding to water. Question? So we said you can have HF hydrogen bonding. Fluorine itself does not hydrogen bond to water molecules, or organic fluorides are not going to hydrogen bond. Those interactions are going to be too weak for that to happen. So we're just going to consider oxygen and nitrogen in terms of hydrogen bonding as opposed to fluorine.
Why not? I don't quite get it.
The explanation is beyond the scope of the class and beyond my scope to tell you, but there is a practical example I can give you. Teflon is an organofluorine compound. It's a carbon chain covered with fluorines at every single carbon. Does Teflon dissolve in water? It does not. Otherwise, your pans that are coated with Teflon would lose their coatings. So I cannot explain it to you, but I can give you that practical example, which you can go test out and find that indeed organofluorines don't dissolve in water. So it has to have either an oxygen or a nitrogen present in order to form hydrogen bonds and dissolve in water. So we'll test this out. I will put my safety glasses on for this demo. Actually, yeah, so let's take a look and see. Okay, can you see in the back? Is our crayon dissolving? Indeed it is. They gave me a nice dark crayon today for this demo, and so you can see very nicely that that dark gray color is going into the hexanes but not going into the water. Okay? So this is useful If you get married and have kids someday and they happen to color on the seats in your minivan or some other place, and you want to get rid of the crayon, are you going to add water? You will not add water. You might not have access to hexane, but you can use gasoline, for example. You just wouldn't light a match, of course. You could use paint thinner, for example. Paint thinner is a non-polar organic solvent, so there are some household products you could use to get rid of that crayon. Okay, so what we're going to do now is we have 4 test tubes with 4 different alcohols in them of differing chain lengths. Okay, and then we also have some water that has some green food coloring in it. Okay, so if we have less than 5 carbons in our alcohol chain, the alcohol should dissolve in water and vice versa. So if I add the water to the short chain alcohols, it should mix. The green food coloring should mix. Okay. But if we have an alcohol with more than 5 carbons in the chain, then it should not mix. Okay, so we'll test this out. First one we have here is ethanol. Ethanol has 2 carbons in the chain. Should the water dissolve in the ethanol? Absolutely. So we'll add some. Okay. I don't even need to mix it up. It just goes right in. Okay. The next one we have is isopropyl alcohol or rubbing alcohol. That has a 3 carbon chain. Should the water dissolve in isopropyl alcohol? Yes, it should. We'll add some and see what happens. Okay. So far, so good. The next one we have is butanol. This is a 4 carbon chain. Okay. Should butanol be soluble in water? Yes, it should. Remember, I told you that solubility is a sliding scale. It's not an absolute either or. Is butanol going to be more or less soluble than our shorter chain alcohols? Less. So it should dissolve. We should be able to dissolve our green colored water in the butanol, but it might not dissolve as well. So let's add some and see what happens. Okay. Yeah, so we see that the water went down to the bottom. I'm going to cover this up so I can shake it around without spraying myself. Okay, going to mix it. Mix it. Okay. Did it dissolve? Okay, but it took more effort than it did with the ethanol and the isopropyl alcohol. Okay, so soluble, but not as soluble. Oh, they really filled this one up. They didn't give me much room. This one is hexanol, a 6 carbon chain. So should my water dissolve in the hexanol? It should not. We should have, what's happening here with the longer chain is the magnitude of the van der Waals forces between the molecules with the increased surface area is going to be higher, have more energy than the magnitude of the hydrogen bonds that we could form between the one OH group and a water molecule. Okay, so the van der Waals forces will be too strong because the surface area in the hexanol will be too great. Okay, so let's add water. We'll just add a little bit more. Okay, sinks to the bottom. I'm going to cover it up with some of this parafilm. Now, I need another piece of parafilm here because I'm going to shake this up. Try to mix it. Okay. I mixed it, but look what happens to it. Okay, I mixed it, but it's not dissolving. You see that it's settling. The green is settling to the bottom. And as we set it down, if we let it sit, and I show it to you again, you'll see that we'll have our clear layer on top and our green layer on the bottom, in contrast to the butanol, which dissolved nicely. Okay? So this guideline in your book is actually pretty good. It is a guideline because, as I mentioned, solubility is a sliding scale. It's not an either-or proposition, but it is pretty good. And you can see firsthand right here that it works reasonably well. Okay? Any questions? Yes, please. Yes. Yes, it's an organic compound, but it is polar because it dissolves in water. Okay? Yeah, we'll learn about dyes later on at the end of Chem 352, but it has to have a highly, highly conjugated structure with lots of double bonds in order to absorb visible light. That's something we'll learn more about in Chem 352. Good question. Yes?
Does the position of the hydroxide groups affect the solubility of
It can, but it's not a huge effect, right? If you had a lot of steric bulk, if you had a lot of carbon atoms around as opposed to being on the end of the chain, then it might impact the amount of hydrogen bonding. But for purposes of the class, it's not going to matter a whole lot. In most cases, we'll just be able to count the number of carbons and the number of functional groups capable of hydrogen bonding to water, and that'll be good enough for helping us to understand whether or not something will dissolve in water or not. Other questions? Okay, so let's look at a couple of other examples of molecules where their solubility properties impact their use and the consequences of that use. Okay, this compound is an ether. It has an oxygen bonded to two different carbons. Its abbreviation is MTBE, stands for methyl tert butyl ether. Whoever gave it that name didn't understand how to name organic compounds because it should be tert butyl methyl ether. So it's kind of a joke, but that's the abbreviation it was given. Will this compound dissolve in water? Okay, I see heads getting nodding both ways. How many carbons does it have? 5 carbons. How many functional groups capable of hydrogen bonding to water? 1. Okay, so it's right on our border. But indeed, it does dissolve in water. It's not going to be incredibly soluble, right? It's going to be somewhere in between these two in terms of how well it dissolves, but it will indeed dissolve in water. In the 1990s, MTBE was used as a gasoline additive. It was added to gasoline to make the gasoline more oxygenated so it would burn more cleanly. But because it's water soluble, those gas tanks underneath gas stations are not impermeable. They do leak, especially when they get old. And so gasoline containing MTBE would leak out of these gas tanks. The gasoline itself would not contaminate the groundwater. It wouldn't dissolve in the water that was in the ground by the gas station. But this would. Okay? Now this turns out to be a foul-smelling compound. So people who had wells near gas tanks or were otherwise using the groundwater near those gas tanks would get foul-smelling stuff in their water. Okay? So they stopped using MTBE as an additive to oxygenate gasoline because it was dissolving in water. It was contaminating the groundwater by gas stations. Okay? Does anyone know what they use to oxygenate gasoline today? Ethanol. Okay? Is ethanol water soluble? It's right here. It's certainly water soluble. It only has 2 carbons in the chain. Most people on this earth don't mind if there's a little bit of ethanol in their water. But before you get too worried about having to talk to your bishop if you have been drinking water from near a gas station, the amount of ethanol that would get into that water is really, 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 really small. So you can still sleep well tonight and not worry about that. But indeed, so the properties of MTBE, the fact that it dissolves in water, caused it to stop being used to oxygenate gasoline because it was contaminating the groundwater. So they replaced it with something that still dissolves in water, but is not going to cause problems. Okay? All right, let's look at another compound. This compound is a member of a class of compounds known as polychlorinated biphenyls, or PCBs. Okay, so this is a PCB. Has anybody ever heard the term PCB before? Okay, one person has. So PCBs were used industrially. They're used as plasticizers, meaning they're added to plastics to give them the right physical properties. They're also used as components of electrical transformers. And what happens, despite the best efforts of people and companies, any compound that's used industrially in some amounts is going to find its way into the environment. Okay? So PCBs, they find their way into the environment. Are they water soluble? No, no water solubility, no functional groups capable of hydrogen bonding to water. So when animals ingest PCBs, they do not excrete them in their urine. The PCBs get concentrated, or they remain in their bodies, and therefore nonpolar molecules such as PCBs that persist in the environment get concentrated up the food chain. So when you have birds of prey, which are usually up at the top of the food chain, they end up with a lot of molecules such as PCBs in their systems. And PCBs cause developmental problems in these birds. They also cause developmental problems in humans, in children, and so they've been phased out. They've been replaced by other less problematic compounds. Okay? So one that dissolves in water and causes problems, one that doesn't dissolve in water, and that also caused problems. Okay? Let's look at vitamins now. So there are lots of different types of vitamins, and I'm going to draw one for you. Let's see, I think I need, there we go. And let me make sure I get these groups at the right places. And in the ring, I think we have, okay. This molecule is vitamin A. Okay. Vitamin A comes from a molecule called beta-carotene that is present in carrots, as the name suggests. Our body chops beta-carotene in half and gives us vitamin A. And vitamin A helps us see. It's also good for our skin, but it also plays a role in the chemistry of vision. That's something we'll learn about in Chem 352. So it is true, if you heard that eating carrots helps you see, that is actually true. Okay? Is vitamin A water soluble? No. 1 OH group and pretty close to 20 carbons. Definitely not water soluble. Okay? So what happens when you eat a lot of carrots? Your body turns the beta-carotene into vitamin A. The vitamin A builds up. It gets stored in your liver. If you eat so much that it overwhelms the amount you need to see and the amount you can store in your liver, what happens? Your skin can turn orange. Has anybody ever seen this happen? We had someone in the last class who said that when he was a baby, the only baby food he would eat was carrots, and so it actually happened to him when he was a baby. I told him to bring pictures in to prove it, but a rare case for adults. Most adults can't eat enough carrots for this to happen, but it is actually possible. Okay? That's because vitamin A is not water soluble, so we're not excreting it. Okay? Our bodies will break it down over time, and we will be able to get rid of it at some point. You won't be permanently orange if you eat too many carrots, but you can eat carrots fast enough to overwhelm your body's ability to metabolize it. In Chem 352, we're going to learn how vitamin A helps us see. It's really, really cool, but we have to wait until we've learned more principles before we can explain that. All right, let's look at another vitamin structure. And running out of room here. Okay. This one is vitamin C, ascorbic acid, present in citrus, has a variety of roles and benefits. Is vitamin C water soluble? Absolutely. It has 6 carbons and 6 oxygens, so it's quite water soluble. Linus Pauling, who won the Nobel Prize for chemistry, but not organic chemistry, I might add, promoted vitamin C as a cure for the common cold. He said if you take massive doses of vitamin C, it's going to cure your cold. To my knowledge, that hasn't been proven. Okay, there haven't been any studies that have proven that. But here's what is proven. What happens if you eat more vitamin C than your body can use? Yes, you will excrete it in your urine, okay, because it is highly water soluble. So while I don't know if it cures the common cold, I do know that if you really want to enrich your urine in vitamin C, you can eat a whole bunch of vitamin C. So if that's what you really want to do, you can go ahead and do that. It may or may not help you with the cold. Okay? Questions? All right. So here is a summary of our water solubility rules. We've already gone over those. Let's look at some other interesting compounds and talk about how their solubility properties affect their uses. Here we have soap. A soap molecule is an amphiphile. Okay, let's raise that up. The word amphiphilic means polar and nonpolar regions present in the same molecule. Okay? So soap molecules are amphiphilic. We have this polar head group, which is a salt, an organic salt. And we have this long nonpolar tail. So when we add soap to water, what happens is the nonpolar tails associate together, and the polar head groups are going to be on the surface of a sphere known as a micelle. And what kind of interactions can we have between the polar head groups and the water molecules? It tells us right here, ion-dipole interactions. Those negatively charged groups can interact with the hydrogens of water. So ion-dipole interactions. You could also say hydrogen bonds, because we do have oxygens here. So these micelles will dissolve in water. They'll go down the drain. And what happens when you add soap to your greasy pan that you just cooked hamburger meat in, and you scrub it, is the grease molecules, which are nonpolar, are going to be attracted to these nonpolar tails. They're going to get inside these micelles, and therefore you'll be able to wash your grease down the drain, encapsulated inside a micelle, even though the grease molecules are not water soluble. Okay? So amphiphilic molecules can form spheres such as micelles because of like dissolves like, and they can dissolve in water. Any questions? Yes? Yep. It's on the molecule because if you have a negatively charged ion, you have to have a cation that goes along with it. Okay? But when it dissolves in water, this will be solvated by water, and then this will be part of the micelle. So the sodium won't be part of the micelle. All right? Phospholipids. We have a polar head group, nonpolar tails. Because we have two nonpolar tails, we get a slightly different shape. Instead of forming a micelle, phospholipids like to form a lipid bilayer, where we have these molecules stacked tail to tail, and then next to each other. So we have lots of van der Waals forces between the nonpolar tails. And then we have the ability for either end of our lipid bilayer to have these ion-dipole interactions with water molecules. So the lipid bilayer forms our cell membrane. Our cell membrane has a lot of other components to it. We'll talk about that later on. Ion channels, these are proteins, but it's going to form a nonpolar barrier to keep ions from traveling in and out of the cell unless that travel is regulated by a special protein known as an ion channel. Okay? So you can keep polar species or salts from getting in and out of the cell with a lipid bilayer. So in the pharmaceutical industry, when you're designing drugs, in many cases, you need these drugs to get inside of cells. And so you have to make molecules that are soluble enough that they can dissolve in water and go through the bloodstream, but nonpolar enough that they can actually diffuse through the lipid bilayer. That's one of the hardest things of being a chemist in the medicinal chemistry industry. All right, last thing, it'll take just a couple minutes. Ionophore. An ionophore is an organic molecule that complexes ions. Actually, it's usually cations, so we'll just go ahead and define it as complexing cations. Okay? Here's an example. Monensin, this molecule is an antibiotic. It has these oxygens in red. These oxygens are Lewis basic. We have to use the proper vocabulary here. These Lewis basic oxygens are kind of arranged in a semicircle around this cavity. Okay? So that creates a Lewis basic cavity that's capable of coordinating a Lewis acid, such as a cation, through ion dipole interactions. We have here a picture of an X-ray structure. It's from an old journal, so it's not very high resolution. But we have a silver cation coordinated to all these oxygens of monensin via ion dipole interactions. Okay? So we have this Lewis basic cavity. The exterior of the molecule, and I should tell you that Me is just an abbreviation for CH3. You'll learn that next week. ET is an abbreviation for C2H5. So the exterior of this molecule, the perimeter, is it polar or nonpolar? It's largely nonpolar. The exterior has all of these carbon-hydrogen bonds. Okay? So an ionophore can coordinate a cation and transport it across a cell membrane, because the exterior can form van der Waals forces with the tails of the phospholipids and pass through a cell membrane. And it can hide that cation in its Lewis basic cavity and transport cations across the cell membrane without the cell's permission, without those ion channels controlling it. And so that's how monensin kills cells. For reasons I can't explain, it's more selective for bacterial cell membranes than it is for mammalian cell membranes. So it's used in the feed of animals to keep the pigs and cattle and other farm animals from catching bacterial infections. It kills bacteria by carrying ions across the membrane. So that's one thing ionophores can do due to intermolecular forces, solubility, like dissolves like. Any questions? All right, we have one more cool molecule to talk about on Monday, amphotericin B. We'll do that on Monday, and then we'll jump into chapter 4. Have a good weekend, stay safe, and make sure you're ready for that quiz on Monday. If you're looking for things to do on the weekend, get started with our sample exam.